So I'm happy to welcome Qinghua Ding to the department to give this seminar, today's seminar. Qinghua, he received his PhD from the University of Hawaii in 2008 and worked on understanding Asian monsoon variability and its linkage with global circulation variability. In 2010, he started to work at the University of Washington as a postdoctoral research associate, and he joined the Polar Science Center there in 2014. 2016, he accepted the faculty position in the geography department at UC Santa Barbara, and that's where he's been. He's visited once before. He thinks 10 years ago.
Yeah, 2013, 14, something.
Oh, really? So it was before your stint?
Yeah, before my job there.
Okay, yeah. Okay, so Qinghua's talk today is entitled Improving Climate Projections and Simulations Through Observation-Constrained Model Capabilities.
Thank you.
Welcome.
Thank you very much. I hope everyone can hear me in room and online. I try to speak up. And yeah, when people come in, so let's see something not exactly about this research, just why I come here. The reason is that the Gudrun and Jingyi, the last time Jingyi invited me, so when I was a postdoc, he invited me, I gave a talk. I don't remember what I talked about, but still climate. So these two persons are really important people in my career development. One thing is that Gudrun, I think my first publication on journal climate was edited in charge by the Gudrun. And Jingyi is very interesting. Actually, he offered me the postdoc job in his department before I accepting the job at UW. So just 1 month late before I accepting that job. So this is the department I really want to come to work like 15 years ago. So when I just heard like invitation by the Gudrun like a month ago, I said, yes, I will definitely come back to visit a lot of old friends. So I think let's start to talk today. And like 10 years ago, I talked about something, still maybe the same thing, like a climate teleconnection. And over the past 10 years, I work with many people here. You can see the name there. And this talk is not from a specific paper. It's just it's something like the big picture. What I think, what I learned over the past 10 years, and what I want to do in the next decade, something like that. Maybe I will give you more like the question rather than like the answers. So I'm using this conceptual plot as my opening like slide. So this is so you can using this one to represent everything. So I use this to think like a global warming phenomenon. So global warming is a big red arrow there. You can think like the big arrow, global warming signal, and this attributed by the many different process. So the point is that somehow we know how much warming we get, but we don't know which one contribute most. So something like that, just something like we know here, but we don't know which one have the largest contribution. So when we do model, we know the outcome. So we match the result, but we don't know the detail. Then we figure out this, we generate a model, then we use the same model to do the prediction. So the main point of my talk today is that maybe we should using observation just like the circulation variability, just like how wind blow from somewhere to other place, using that as a key field to constrain model capability. By using this circulation as a constraint, maybe we can move closer to a better model. So this is the main idea. So I don't have a lot of slides. I only have like a few 10, 20 slides. So please stop me and anytime in the middle of my talk. So this is the key figure from recent IPCC report. So there's a three rows. So you can see that one is the annual like hottest day temperature and soil moisture or precipitation. So if you look the total report, the whole report, like take like 80 pages. If you read the whole report, you don't find any figure about circulation. So it seems like the circulation is variable many study still think that it's not that critical. There's so many reasons. The one reason is that circulation means like atmospheric circulation. Atmospheric circulation, people think that is something like a transient process, just really move really fast, okay, and doesn't carry any memory. So the most important variable could be ocean temperature, or could be like a precipitation, because that is the close to our like the ecosystem, to close to our everyday life. But I think that if we want to know model better, we really need to make sure model get circulation pattern right. So still it is a plot, because if you go back to the very original equation, like a temperature equation, the temperature change is we know that determined by three key processes, right? Like a horizontal temperature advection, vertical adiabatic process, and diabatic heating term. But diabatic heating term includes so many terms, right? So, and heating cannot be measured. Heating can only be calculated, right? Because if we know the temperature change, so we do the opposite way. We know the temperature change and like a temperature tendency, and we know the advection effect. We know the warming due to the vertical adiabatic process. We calculate diabatic heating. That is how we understand diabatic heating. It cannot be measured. So that is the main problem. We're using like the many the scheme, right? We call the parameterization scheme to simulate this diabatic heating, because that is diabatic heating is the big term in our model, right? Like the radiation, like convection, and many process contribute to this diabatic heating. So that is the issue, right? Because we don't have a lot of power to constrain our model, especially the simulation of this diabatic heating term, because so many processes there. Now in IPCC 6, one key issue is that model become warmer and warmer. People realize if you're using all the model together, like treat them equally, and it's different. It's a little bit harder than the IPCC 5 using the same way to treat the model, right? And people somehow figure out this is due to the maybe cloud is not well simulated or something else. It's a very complex problem, and but when we look at the model, like IPCC report or this summary page of this model, you always see this figure, just like the global mean surface temperature, right? And the black one is observed temperature over the 150 years, and the red one is the model false by this the anthropogenic falsing, and the other one is the natural variability. So because you only look the total average, right? And but if you also look at the Arctic, Arctic is the right panel. That is the Arctic sea ice melting in September sea ice. The right one is observation, and the other color is model. So you can see if you look at using different metrics or focus on different variable, you find the model performance is really different. If you look at the global mean, you feel model is perfect, right? Give you whatever you want, or give you like something we try to understand. But if you look at the detail, look into the like a small domain, small area, small region, you find actually model may be a little bit cold to capture like a CS melting in some region. So that is something puzzled me for quite a while in past years. Model too hot in some region, or too cold, or rain too much or rain too less, something. But if you look at the global scale, looks pretty good, because we know the performance model depend on how we measure their capability, right? Performance vary. So next is the example I want to give you. So maybe take some time to talk this plot. So this is 9 panel. So to the left 3 are observations. So that is the top one is the circulation. We call the potential high at the upper level. So that is just like a potential high, just like how the air column warmed. You can think of it that way. And the middle one to the left, that is the middle level, potential high, and the bottom one is the surface temperature. Okay, 3 panel, circulation, potential high, different level, upper, middle, and the surface temperature. And the middle 3 and the right 3 are model result, different model. All the model, you just add them together, and look the model response to CO2 forcing. Same variable. Okay, upper one still circulation trend, and the middle one is the circulation in the middle level, and the bottom two is surface temperature. Or reflect so to your let the three reflect observation. Okay, you can think that observation over the 40 years, annual mean, or something like that. And the same variable, same configuration from model result, forced by CO2 forcing. Okay, so if you look at the previous slide, you will see very similar plot, like this black curve, right? Just like if you do global average, you find it's pretty good match. But if you look at the spatial pattern, you find it's very different actually, especially circulation. If you look at circulation, upper three, okay, upper column, okay, upper three, you can see in the model, the maximum, the rise of this height actually occur in tropical region. That is the red color in the tropical region in two large sample model result. But observations show the largest rise of the potential height actually in the polar region, especially in the Arctic region, and the negative in Antarctica. Okay, model with forced by CO2, by ozone, by aerosol, model cannot capture this. Okay, and if you look at the surface temperature, you also find it seems like the model is the less warm. It's a little bit cold in the Arctic region, and there's no cooling signal in Antarctica. But the observations still show more complex feature. If you do average, actually all is a signal just wash out. Okay, so when I first saw this plot, I think that this pattern tells us something, because the circulation change tells us in the real world. Okay, just left the three in the real world, you have a high pressure above and the warming surface. That is we call some structure called a barotropical structure. But in the model world, the surface is pretty warm in the Arctic, but the upper level is moderate. It's not that strong. So that is the different structure. Different structure means the different dynamics. So that tells me just the part of the warming in the model is a little bit different from it's supposed to be in the real world, because dynamic different, because circulation structure is different. Okay? Circulation is important. Circulation tells us how the system operates. So that is what I think why we need to using the circulation as a key field to evaluate the model. Because currently in IPCC report, if you look at the whole report, there's no figure or no single plot to illustrate how model captures circulation variability. Then let's see the both. So we know this plot, right? So there's so many model you can run many times, but we only have one observation that is shown in next right curve. Only one realization as observation, and we know observation contain both forced, like a CO2 forced signal, and internal. But a model, if you run many times, each individual member contain both. So we don't know how to compare model with observation because they look different. So the only way we can do is that we increase our realization. We run many times. We get so many, like a spectrum, like a many thin, like a blue curve there. And we just average them, just like a thicker blue curve that is represent example. When you do this, basically the goal is that we try to remove internal variability. Okay, because we think internal variability somehow is like a stochastic process. And we try to match this the big blue, thicker blue with this observation. Okay, but when we do this, it's hard, right? It really depends on which variable we want to look at, right? Still the same thing. We know so many issues there. Internal and false signal are model dependent, and they differ, right? So another case is that recently I tried to work on this signal prediction stuff, but if you look at the current performance of all is a model, the best model summarized by the IRI, you can see this is like a scale of current, like in sample mean something, and this is for the precipitation for different season, and just like like 2 weeks ahead, okay, leading time, you can see for the precipitation for many regions, this scale is pretty low, especially over like a western United States and the high latitude region. Okay, we know over 30 years, people have tried a lot to improve their model, but still model have a lot of room for improvement. Yeah, so I've talked about my idea. So you know the idea, just very simple, just try to focus on circulation because we know circulation tells us dynamics. So next I will show you two very simple examples, just show how to apply this idea to solve some issue. So one is for the Arctic, because we have a lot of people working on the polar region. So the second one is to understand like a winter precipitation change or like a prediction for the United States. Yeah, so this is the, so any question before I go to the, okay. So this is the September total CS area from observation, from satellite data over like 40 years. So you can see in the early period, it's kind of a slight decline trend, and suddenly there is like the abrupt change for like 6 years, 7 years, from 2020 to 2000 to like 2012, something like that. Very recent 10 years is pretty interesting. It's kind of like a pulse like stuff there, right? And but based on our understanding, we know there's a really important feedback there to amplify this. That is the albedo feedback, right? So that means that if 2012 is a big melting year, so that feedback will kick in to further amplify this melting. But we don't say this in observation. We find something just to stop and just stay there, right? So our current physics cannot fully understand this because all physics is positive feedback, just to amplify that. We don't have a lot of negative feedback in polar region to explain why the sea is just a kind of just a stop sign. So I think that in the future, like the next 10 years, if we really want to understand why we had this historical record, there's two like a bifurcation, like the pathway. One thing is that if everything here is forced by CO2 forcing, it's pretty easy to forecast the next 10 years, right? Just like a red arrow, we will see really rapid CS melt, right? Because if over the past 40 years, CS dominant, 99%, next 10 years, we will see the same thing. But if over the past 40 years, some part of it is melting due to internal, so maybe we will see something minor recovery or like a slowdown of the decline. So we don't know that. So the goal of this part is to see, we try to using some additional constraint to improve our prediction or projection in the next 10 years for sea ice. This is not a very new idea, actually. Many people have proposed this, and this is a two recent paper, and they just argue Arctic warming. You heard about term, right? Arctic amplification. So that means that it's warm faster than the rest of the globe. And but if you look at the model, different model. So this is the red one is they call the AA, Arctic amplification parameter. Just means that using the Arctic warming trend divided by the global mean warming trend or something. So normally you get the observation, we get this ratio is close to 4. But model cannot get that strong like warming like ratio. So observation like pretty strong, especially over the past 10 years. And the model always give us something like a dash line, it's like a 2 or 3. So even model improve a lot, but the model still underestimate warming intensity in the Arctic region. And this another study also argue is the model warming in the Arctic is too cold compared with observation. So this is the one slide to summarize what I found over the past 10 years, why Arctic warms so fast, but show very strong like the step-like feature, just like in the early 10 years is kind of a slow, but suddenly have a decline, and then there's the leveling off again. So my argument is that over the past 40 years, there is like the teleconnection that is driven by some tropical forcing in the polar region, in the tropical region, and this teleconnection propagate into the Arctic to drive this warming. The process is pretty simple, just like there is the cooling trend, ocean temperature cooling that drive a wave train, and this wave train will tend to propagate like the poleward and generate a high pressure over the Arctic. And this high pressure is quite barotropical structure. So that is what I show in the beginning slide. In observation, you find it's a barotropical structure, high pressure above, high pressure in the middle, and high pressure in lower troposphere. In model world, you don't see this. It's forced by CO2 forcing. And if there's a high pressure built there, just like the heat wave, right? Today, maybe it's governed by heat wave. So when there's a heat wave, the air sink, subsidence, adiabatic process, warm air, and favor long wave radiation to accelerate this like melting. So this is based on like 40 years like process. But if we look some like longer data, so this is something we get from longer reconstruction data, 400 years data, you can still find a similar wave train pattern. So some cooling here and low, high, low, high. So this is not over the 40 years. It's kind of some pattern over the 400 years. And this is the 400 years like a time evolution. So you can see this is a recent one. Okay, I just using some big one because the data stop around like the end of like the 20th century. So I don't have a new data here. So this is new data here. So you can see, so this is 1980. So if you only look at recent 40 years, it's just a very end cycle of this long period. Yeah, so you can see this is a recent one. And if you put this time series, this circulation time series align well with our sea ice, this circulation connection pattern is somehow just stay in some level and suddenly jump over this 12 year. If you match this circulation pattern with our sea ice, you find somehow there's a pretty good fit between two time series. Just when circulation change, with a circulation or high pressure completely build up over Arctic, that favor very significant melting. Yeah, melting over this over Arctic region. Yes.
Well, could you explain more about that 30 years period? What does that mean?
Yeah, 30. Just we calculate this periodicity. It's a 400 years of data. We find the dominant frequency of this oscillation is around like 30 years.
So that one has a 30 years.
Yeah, 30 years frequency. Yeah.
And do we know what produced that 30 years?
I don't know. Yeah, I don't know that. Yeah, maybe IPO or PDO or something else. Yeah, it's just like some low frequency. Yeah, it's definitely not ENSO, right? But it's something like the low frequency variability in the tropical Eastern Pacific.
And your previous schematic indicator that almost started with number one, SSD cooling in the Eastern Central Pacific.
Yeah, Eastern Central Pacific.
So what is that phenomenon?
I don't know. It may be CP. I don't know what's that. Yeah, because. Yeah. Yeah. I only focus on the how this applies. So I think it's good to know, investigate the cause of this mode. Yeah. Thank you. Yeah, but the point of this slide is to tell you what my understanding why we have this type of the change, the sea ice over the past 40 years, because this phenomenon, if you only look at this longer data, is only takes this end period of this. But if you look back beyond 1980, actually you can see it's up and down many times. Yes. Yeah, I'm using some data called, there's a bunch of like a reconstruction. So this one is the Germany version, EKF. Yeah, I don't remember. Oh, EKF 400. Yeah, we also check the different reconstruction. We find a similar mode. Yeah, but this is not a completely observation paleoclimate. It's kind of like the mixed, just like the blend model result with some paleo isotope data together, and to improve this model simulation. Yeah. So that's why you can see if you look at the time period is a little bit this high frequency, maybe due to the like less data there. right? Because over recent 100 years, we have more data, so give a more like a reliable resolution or reflection of this feature. Yeah. So that is so based on this, if my result is right, that means the circulation really matter, or this mode is really matter, and this mode is internal because we see this mode operate, okay, and up and down, move up and down in the past 400 years. So it's not triggered by the anthropogenic forcing. If we believe this is right, and we should use this one to help us constrain model result and help us to do the future projection. So how we do this? So we're using something we call this observation constraint. So this another way, another two pathway available. So this is the most used way currently by the community. One thing is called a model democracy, just so everybody treat the model equally, right? Another one is just to select the best model. This selection really depends on I have to say really subjective. Just the point is that we really want a model match 40 years data. Okay, you just match a model with 40 years data. Then that group we call the best model. Then using that model, that group, subgroup to do the future projection. Okay, so this is the current two main thought to do this. But I think maybe we can consider the third path, just like we can remove internal variability from both, then compare the residual part. Because the idea is that we know circulation is important in observation. And so let's remove circulation-driven warming from observation. Okay, so that means the left part, the part left is something forced, mainly by forced. Then we do the same thing in model, also remove this circulation-driven part from model, then compare both. So that is more like a compare apple with apple, rather than like compare apple with orange. Okay, so that we call the observation constraint one. Okay, just remove internal variability from both model and observation. Compare their like a residual part. Okay, this residual part, if they're equal, that means the model have a good sensitivity. If either one is larger, we recalibrate model based on this residual component. So this is the main idea. Yeah, because the issue of the second pass is that if we really want to match observation, I mean the false one, right? In sample mean with observation, we assume everything observation is false. But this assumption is not 100% right for different domain, different region, right? So that's why I think we should use in the third pass, just like to remove internal from both, then compare residual. With that way, maybe we can just step closer to the real sensitivity of a model to anthropogenic forcing. Yeah, so this will give a really different result. See, if you're using the second one, because you want a model match this red curve, so definitely you will get something melt faster in the future, right? And so that's a very natural result. So the second pass always give our model very sensitive, because the observed record is faster than the model give us, right? So that's natural give us. But I think probably we should think the yellow curve, that one, just remove internal from both, then compare residual. And by doing that, we find actually model still too hot, okay? And the model still too hot, we correct that. Then we find actually model should give us like delay melting or delay emergence of this ice-free time. So that is the yellow curve project too over this time period. Okay, rather than the red curve give us like the 10 years before is the example mean. So this is give you some what time. I will show you, yeah, next step. Yeah, so how to remove internal, because we know the circulation is important. So here we're just using some like a stream function over some region to represent like a wind change. Because we know the anthropogenic forcing doesn't favor, wind change is related to pressure change, right? But CO2 falls in quite uniform, doesn't change the pressure gradient, so it doesn't change the wind too much. So we're using the stream function, just like a wind, how the wind blow, right? Like a rotation component. We just use that one over some domain as a represent wind forcing. We remove this from observation, but regress out, simply regress out, and also regress out from model. And compare so we call something like this. So we just remove this stream function related to warming from observation record and compare with the raw trend. We call something like a ratio. So if you look at this plot, we find, so there's the left, is the y-axis and the x-axis. X, this is a raw trend. This is a residual trend, okay? And so that means that if you find some point of fall here, that means so along this diagonal line, that means that it's a half. It's the ratio is 1, right? And over this sector or over this half, that means residual trend is less than like raw trend, right? Because you go that this line just move anti-clockwise toward like this side. Okay, so this color dot just means this is the real analysis. In real analysis data, if we remove stream function related to warming, all this trend become weaker. So you can see this is stronger and this is weaker. Let me see this plot. Oh, sorry, I said something wrong. This is a raw trend. This is a residual trend. So if see,
You're not seeing the mouse on there.
oh,
Are you using the mouse?
yeah. Yeah, so see here, I cannot see. Yeah, so this is a raw trend. This is a residual trend. So x-axis is the raw residual trend. This is the raw trend. Okay, so let's see this point over Arctic, and the raw trend is this value. But if we remove that, the residual trend is smaller. So that's more the points fall in this half. But all the model, if we're doing the same thing, the model doesn't matter. Still stay in the same line. Okay, it's diagonal line. Diagonal line just always a 1-to-1. We do the different variable, different season. All the observations show this movement from 1-to-1 ratio line to something less than 1-to-1. But all the model, even we do this, no change. So that means like if we remove like stream function related warming from model record, no change. So for all the models, this ratio is 1. For observations, the ratio is something like the 50%, 70%, 80%. So that means that this stream function related to warming just take like a 30-40%, depend on the variable and the region. And the model is 100% always. So that means in the model world, circulation doesn't matter. Just circulation doesn't drive any warming, doesn't drive any long-term change. Yeah, so based on this, we adjust this, and find we give like a 10-year delay from example mean. Yeah, this is just a plot tells us that. Yeah. Another plot is that why the model doesn't favor this circulation-driven warming in the model as observed. We think the reason is that the tropical SST. So this is the plot with different season, like a JJ or annual mean. And to your left, like a thing, this one is something like the observation. And this is you cannot see the plot here, but this is the observation, ERA, and this is a different model. And this is for the different frequency. The point here is that if you look at observation, and you find low frequency variability take a lot. Oh, yeah. Yeah, can I? Yeah. So let's say there's a plot, right? The left upper corner. Okay, left upper corner is the observation, right? So that it tells us like the variance of a low frequency ST over the total variance of ST, something like that. And you see over like the like the region from Central Pacific to like a Baja coast is pretty high. It's a red color. That means it's quite a lot. But the model doesn't give us this. This is a model. The two panel below that top one is a model simulation. So you see, in a model, model doesn't favor low frequency variability over the region. Okay, but in the real world, it's a very strong variance from 8 years to 40 years. Okay, so this is for JJA, and this is for annual mean. And yeah, to your right, that is the ENSO. The red color is the 2 to 8 years. So to the left is the low frequency, to the right, that is the high frequency. Okay, so models seem to capture ENSO pretty well. ENSO, like the contribution, but weakly to capture is the low frequency variation. Yeah. Yeah, the reason, so things ENSO cannot, so low frequency mode cannot well capture, so teleconnection cannot well capture, so tropical forcing cannot easily propagate to the Arctic region and cannot apply the local forcing to melt sea ice or warm the Greenland ice sheet or something like that. So this is our idea. Yes.
So when we average all these models together, specifically just go to all the signals. So could that be like some models that are doing well and some models doing that good? And do these like the model doing a relatively better job?
Yeah.
Can reproduce this?
That's very good. So that's the lead to my next plot. So you ask, so this is observation. So in observation, we know there's a two leading mode, right? It's the teleconnection. One is the PNA, one is a mode. So if you see this, the middle panel, so cooling can drive some teleconnection. So I did this. I just give a Fourier model, give some like a statistical method we call the SOM, right? Just like the self-optimization map. I just want this method tell me which model can do better than other models. So you can see if you put a Fourier model there, so the upper one, so there's a 6, you can see like a 7 small plot. The top one is observation. Another 6 are all from model. So you can see any model can capture something similar as observed. So this top one is something I want a model to capture. That is so the top one, the two small panel. One is the teleconnection, right? The middle one is the SST. So you see some tropical cooling, the green color, tropical cooling can drive some teleconnection to the Arctic. So with a high pressure over Greenland. So that is the big blob, like a bullseye, like a right one over Greenland. Okay, that is the from observation. But if you look the 6th panel below that, no model can do that well. Okay, except one something like in panel, I don't know, in panel F something. That's only one out of 34 model. So it seems like the model cannot do really well to capture this. And we find some reasons. That is we checked the different feature field. We find limitation in mean state and or like the low frequency SST. And that relate to some like convection because we know the rainfall change is a forcing to drive. Diabatic heating is the driver teleconnection. So model have a limitation, and no model can do that well. But I don't know why, and I don't know how to improve that. And I still have like 5 minutes, so I want to use a few slides to talk about another one. Quickly talk about this one, just like we know circulation is important. So I want to show another case is that we want to see how circulation drives the rainfall over this area. And we know the ENSO is the key thing, right? People always talk about the ENSO. ENSO is the driver and the United States. And if you look at the future and people say, oh, ENSO get more active and maybe more rainfall over some area. And this is the IPCC report again, you can see, and the 4-degree warming. And so I can see my mouse. So if you look at the climate, the left lower panel, you can see this is the climate average, just the total precipitation change under like a 4-degree warming scenario. So that projection tells us California may see more precipitation in the future, right? When our world is warmer. But I do something differently. I still like to see how circulation drive precipitation. So I do something a little bit complex, but pretty. I just to give you an idea. Just here, everything is observation. Okay, from observation from 80 years data. 80 years data, and I looked at how circulation connect with the AR. So to the left, you have the total have a 4 column, right? The leftmost column, that is the connection between circulation and the AR. Contour is circulation, shading is the AR. Okay, and the one to the next to the right, that is the time series. So you see, there's a 4 leading mode over this area. Okay, so circulation will drive AR, and AR will drive a rainfall. That's it. And the third column, right? That is the rainfall change. So if you know how the circulation drive AR, and you will see how this mode connect with the precipitation, you try to look at the third column. You see the third mode, that is in the third row, you see a lot of precipitation change over Western United States. Okay, the first row, that is the ENSO mode. If you see the first mode, that's the ENSO mode, but ENSO doesn't cause a lot of rainfall change over Western United States. The second mode is a global warming mode. You can see from their time series in the second column. Okay, the third mode is a pretty important mode. That is really key to drive the rainfall change over Western United States. The fourth mode, the bottom one, that is the one induce some rainfall change for like the Arizona or New Mexico state. So this everything here is for winter time, okay, for 80 years. And to the right column, that is the global map of this circulation. And the shading is the ocean temperature, and the contour is circulation. So you can see the first mode is definitely very classical ENSO pattern, because you can see ENSO there, El Nino there, and drive PNA pattern. And the third row, you see nothing there, just like a short wave train and no tropical SST something, right? So my argument here is that the rainfall change over the United States, especially over the western part, have nothing to do with any external boundary acidic forcing, and also have nothing to do with this global warming signal. Yeah, so I do the same thing in CSM2. CSM2 have a future projection, so I'm using like 250 years data to do the same thing. You can find this. The leading mode, the first one, going up, just like the overshooting, right? You know that the CO2 driven. Okay, other three just vary, quite like internal variability. The time series is start from like 1850 to 2000, like end of the next century, end of this century, 250 years spanning. Okay, and this mode, the mode I talk about, really important for Western United States. Actually, it's the last one in this plot. Okay, you see there is low pressure over the Western United States, and there's like AR moving, and but if you look at the time series, it's just flat over the 250 years, and there's strong CO2 forcing. So that is what I found from model results. From this, I can tell you something I learned from this experiment or this practice. Just like there's so many modes in observation drive a rainfall change, and the important one is the one in the third row, right? And this one can be captured pretty well in model, but it seems like it's quite insensitive to significant CO2 forcing. So that is my main conclusion based on this part. The large scale circulation pattern are, this pattern important for Western United States rainfall is consequence of something like a stochastic instability of a basic state, rather than driven by ENSO, El Nino, or a tropical ocean temperature, or extropical ocean temperature, or global warming. Probably in the future, next couple of decades, this model will keep doing this and bring some resilience to the climate change over this area. I mean, just only talk about precipitation rather than the temperature. Okay, so because we know the precipitation change is really complex, right? It's sensitive to the how much moisture just moving in by the some like system, like a weather system. Yeah, this is my final slide. So the main message is that circulation is important. We try to, and we should understand this, use this as like a matrix, one part of the matrix to evaluate our model in the future. Yeah, to end my talk, I also want to bring up some additional thought for either discussion or like a future study. Just like maybe there's another way to evaluate a model, not only using the circulation, maybe using the additional field. And another thing is how do we know model, how to use the model to understand the observation? It's another issue, right? Because somehow there's a circular thing, right? We're using the model, we use the observation, evaluate the model, but the goal is not using model to understand observation. So we need to find how to get a balance or how to find a solution to do this. And in terms of its physical process, I think it's very complex. So like what is the dynamic origin of this like 30 years periodicity variability? I don't know. Maybe some low frequency mode come from the like subtropical to the tropical region, and we don't know how good a model is to capture how good a model are in capture this process. And yeah, so that's it. Thank you.
I want to make sure I understand your argument correctly about the Arctic sea ice melting. You're saying the recent rapid melting of Arctic sea ice could be a result of that 30 years situation mode. Is that the argument? Because
Yeah, kind of. Yeah.
High pressure over in the Greenland area and quickly melt the sea ice. That's what we call PARC pattern.
Yes.
And PARC pattern can be a saturation change.
Yes.
Doesn't associate with any SSD change. Or we didn't say that.
Yeah, we think the recent 40 years, 30 years, this circulation pattern could be driven by cooling over the tropical Pacific.
Okay.
Yeah, then this mode is not new over this 30 years only. It reoccurred in many times in the past 400 years.
So coming another 30 years, it may reverse the fate, and then sea ice will.
If this mode is if this mode is a real mode, it's a stable mode, it should. So that's why I said why we had this type of a leveling off, and maybe we have to see some minor recovery, because at the same time you also need to consider CO2 forcing, right? That is the background warming.
So the argument is not go along that pool.
I don't know, I just gave an idea.
PARC is the reason, and we make go with that pool.
Yeah. If we consider that.
You still don't know the source of that 30 years.
I don't know that.
Because
Yeah.
if it is circulation by itself, there's no way an atmosphere can produce anything with a 30 years periodicity, right?
Right.
It cannot be.
Yeah, but
inside the atmosphere, right?
yeah. But the one issue for this 30 years period is based on this 400 years of data. But this 400 years of data have some uncertainty because of paleo record just bring in there, and due to the like a sparse resolution early period. So I don't know that part. Yeah.
That's right. Then if you look at a historical sea ice record, you should see excursions of that magnitude in the last 30 years.
The people, I didn't do that, but some people say there is a pretty strong interdecadal variability in some proxy record of sea ice.
Right, and you should be able to look at covariance between the sea ice
They're
record
very
and the atmosphere.
uncertain. I mean, there's almost no variability in the sea ice record with satellites. If you look at variability,
That's what I thought. But I'm saying it should be very strongly in that record.
Yeah, but the sea ice is pretty hard to find the direct proxy, right?
yeah, it's a very difficult
Yeah, using something using drifting wood to.
But wouldn't you see this oscillation even in, in the analysis from the 1850s or whatever?
Yeah, we can see that in
You do
real.
see that?
Yeah, we see that.
Okay.
Yeah, over like 100 years, we can see that using like a 20th century, ERA 20th century. Yeah, we can see that.
Is this a summertime teleconnection or is it? Why do I have in my mind that it's related to summertime?
It's a summer.
Oh, that's it.
Yeah.
Well, and it's because of your previous paper on Greenland melting, right?
Yeah.
So it does say something.
Yeah, I think maybe it's the year-round event, but the effect, the impact may be more prominent in summer because of the melt stuff.
But what could be the physical mechanism? I mean, only.
Because the wintertime is pretty cold, so a little bit of warm doesn't matter, right? -40 and -40, 35, we cannot see the impact. But in summertime, freezing point, just a 1 degree warming can generate some pretty strong result, outcome. I don't know, right? Just
Any other questions?
I don't know. IPO is like 60 years, right? I don't
It's
know.
like 40, yeah.
40 years. Yeah, I don't know. Because the main thing is that the data is short, right? Relatively. I mean, the instrumental data is short, so it's only 2 cycles, 3 cycles. How do we know? This is 60 years is robust, 40 years is robust, right?
I just want to mention one thing. This pattern show up very often. If you look at the signal graph in 2013 and 16, the graph, the Z400 or Z500 down to the signal graph, all the bars that you see almost exactly the same as pattern. In the past, this was sometimes in the Pacific area, you see a wet trend, right?
Yeah.
And then over the North Atlantic, you see a more like north-south cycle. This pattern, sometime in the past, in the 1980s, was named PNX.
Okay.
Tropical Northern Hemisphere pattern.
Yeah.
That's exactly what if every source remember as well. We argue this pattern caused the marine freeway over South Alaska. So what I want to say, this is probably something like a normal mode of the Northern Hemisphere situation. So it could be excited by shorter forcing become marine freeway.
Yeah.
And it could be something to afterwards a 30-year curiosity. I just want to say this pattern caused North Pacific to North Atlantic show up very often in the Northern Hemisphere.
Okay.
Which is interesting.
Yeah, thank you. Yeah, I'm trying to.
Not with this time span of 30 years or 30
No, it's a bit of a marine fuel is just a one year.
Questions, comments? Yes, Jim.
When you're doing a summer prediction, are you
You mean large ensemble?
Yeah.
I didn't do any large ensemble. I think I'm user of the data set. Yeah, I think they just initially perturbed the model by the atmospheric, just some temperature minor change somewhere. Yeah, I think they're using this way. Very small change. Right.
How do you check that the high resolution simulation because high resolution is specific? I mean, there's a simulation of this.
Yeah, I haven't, but yeah, I think it's good to take a look. Yeah. Yeah, but still, the issue is that the reason is that even you get a model, get it right, you don't know why, you know? Yeah. So we want to, yeah. But you're right, we should check it's depend on the resolution or not. Yeah, we should check it first. Thank you.
Okay, thank you so much.